Alright, so the last section we're going to look at is period changes. Okay, so it's still 2.4, just part 3. And up until now, when we draw all of our graphs, okay, they might have looked something like this. How many radians did we have to go through to get from the beginning of one cycle to the end of one cycle? What's been the width of one cycle? Yeah?
5.
Not well. I guess there's 5 points. 1, 2, 3, 4, 5. So there's 5 points we have to draw. But if I were to measure,
Yeah, but the distance between each of those points was 1 radian.
it's not 1 radian. The distance between them is, remember, we don't label that 1, 2, 3, 4 on the x-axis. How have we been labeling it? Yeah?
You end with 2 pi.
You end with 2 pi or 360. So we've pretty much always been looking at one cycle of the graph, starting at 0, it ends at 2 pi. Or if it shifts, that's fine. Like if it did something like this, I don't know why I have 2 of them, but if it shifted over, might be easier to just use the other one. So if you took this graph, I'll make it a different color so it's easier to see. Make it green. If you took it and you shifted it over like that, it's still 2 pi from here to here. Okay, all you've done is slide it left and right. So we haven't done anything like that, actually squishing it, okay, horizontally. So that's what we're going to look at today. Okay, we're going to be changing the period, or the amount of time it takes to do one full cycle. We can make it a longer cycle, or we can make it shorter. It depends on what number we use. Okay, so we'll start off with how a period change looks. Okay, and basically a period change is just when you put a number in front of x and its multiplication. Now the book uses, for this one they just happen to use a Greek letter. I know I've used A for amplitude. I think I used D yesterday for something. But they use this Greek letter. It kind of looks like a W, but kind of loops on itself a little bit. It's just the Greek letter omega, but it just stands for a number. So like sine 4x, cosine 2x. So the key with a period change is its multiplication. But it's different than amplitude. Amplitude, where would the number be when you do an amplitude change? Yeah? Before it would be in front like this. That's multiplication in front. This is multiplication inside the parentheses. Okay? And that makes it a period change. Okay, so let's graph sine x and sine 4x. Okay, I already told you kind of the idea of what's going to happen. It's going to stretch and compress it horizontally. Do you think the 4 is going to stretch it out and make it like a longer wave? Or do you think the 4 is going to compress it and make it like a shorter wave? Longer? All right, well, let's check and see. Remember I said there's 2 transformations that do the opposite of what you would expect. And this is the other one. So the bigger the number you put in front of x, the more, actually I can zoom in so you can see it a little better, the more and more compressed it's going to get. The one in red is 4 times as compressed as the one in blue. So if you look at the graph, just make it big for a second. This is one cycle of the blue. If you trace the red graph in the same space, okay, trace it from here to here, watch how many times it repeats. 1, 2, 3, 4. So that's where the 4 comes from. It compressed it 4 times as much. So if I put like a 10 in there, you would get, it would compress it even more. You'd get 10 cycles. And at that point, it gets kind of hard to see because it's so squished together, you can't even really see them anymore. can kind of see them. Right? But they're starting to get so squished, it's hard to see. Yeah.
Wouldn't the 4 whole cycle be pi over 2?
Oh, for the red one?
Mm-hmm.
One full cycle? We're going to talk about that because we've changed the cycle. So part of the problem is going to be figuring out, okay, what did we change it to? Well, originally, the cycle was that much. We shortened it by 4 times as much. So it would be exactly what you said. Yep. One full cycle now is right there. And that's at pi over 2. But we'll talk about that. But yeah, it's good. All right, I had some other ones too, which I erased. Let's see if I can put those back. All right, so cosine 2x, that would compress a little bit. You'd get double the amount of cycles as the original in the same space. Now, what about sine 1/2 x? What do you think is going to happen there?
Make it longer.
Yeah. What it's going to do is it's going to make it longer. Put 0.5 because that's easier to type in than a half for me on this. So what's happening now is it's doubling the length of it. Okay, that's how you think of it. 1/2 makes it twice as long, where 2 would make it twice as compressed. Okay. So all the graphs today we're looking at are either going to be stretched or compressed. You've already seen that along the x-axis. So this is the last transformation. We stretched and compressed on the y-axis. That was an amplitude change. We're stretching and compressing on the x-axis. It's a period change. We've shifted left and right. That was a phase shift. And now we've shifted up and down. That's a vertical shift. So now we've done every transformation that we can do. So the key, whether it's going to be stretched or compressed, is this number right there. What do you think that number has to be bigger than for it to compress?
1.
Has to be bigger than 1. So if it's bigger than 1, it compresses. If it's between 0 and 1, like a half, a quarter, a third, any of those would stretch it. Yep. Yeah, just okay. Now you might say, well, what if that's not W, it's omega, but what if the omega was negative? We're not going to deal with omega being negative. If you remember what a negative does, what does a negative do? It flips it. Well, if you put a negative in front, it flips it up and down. If you put a negative inside, like that, it would flip it left and right. So one of them flips it over the x-axis, up and down. One of them flips it over the y-axis, left and right. So we're not really going to look at omega ever being a negative. So you don't have to worry about it. Any questions on that? All right. So since we are stretching and compressing it, we're changing the cycle. Okay, we're changing the period. So we're going to have some questions that don't ask us to graph it. They just say, find the period. Okay? So it'll be a question like that. Find the period of sine 2x. All right? So to find the period, okay, t, it's the letter our book uses, that t stands for period. You take the original period, which is 2 pi, that's the original width of a cycle, and you divide it by whatever number is in front of x. That's the calculation you need to do to find the period. I'm not sure if that's how Joe did it, but he already kind of figured it out for the first one. I mean, if you just kind of think about it, if you're like, well, if you started with 2 pi, and I said, all right, you're going to compress it twice as much, that means it's going to cycle twice as fast. So if it was cycling at 2 pi, if it's going to cycle faster, that means it's cycling in a shorter amount of time. So it would be 1 pi to do a full cycle. So let's try this one. So find the period of sine 2x. And that's kind of like what I just explained. Right? So you always start with 2 pi in the top. And what's omega in this problem? What number? 2. Okay, I want to be clear that that number that I just circled, that's not the period. That's omega. It's part of the formula to find the period. But you have to make sure you do this calculation. That's the period. What's 2 pi divided by 2? Pi. So what we're saying is if you draw sine 2x, it'll do a full cycle by the time it gets to pi. Versus the original would have needed to go how far to do a full cycle? It would have had to go to 2 pi. So this one is cycling twice as fast. Okay? If you want to think of it in degrees, the original has to go all the way to 360 before you get a full cycle. This one only has to go half as far, 180. Any questions on that? All right. Let's try this one. Cosine 5x. So what's going to be my numerator in the calculation to find the period?
2 pi.
2 pi, that never changes. Numerator is always 2 pi. The denominator is omega. So what's my denominator? Christian? Yeah, and this time it doesn't change. I mean, it doesn't reduce. So that's your period. Okay. And that's shorter. How much shorter is it than 2 pi? 5 times as short. So this graph is cycling 5 times faster than the original. If you wanted to think of it in degrees, that's 360 divided by 5. So this graph is cycling every 72 degrees. You're getting a new cycle. Versus the original was every 360. Okay. Any questions on that one? All right, let's try this one. 1/4 x. What happens when you put a fraction in front? What happens to the cycle? Does it get longer or shorter?
Shorter.
It stretches, gets longer, right? So now I'm expecting a number bigger than 2 pi. So let's see what happens. We have 2 pi, which this time I'm just going to write it as a fraction. So 2 pi divided by omega. What's omega in this case?
1/4.
1/4. When you have a fraction divided by a fraction, what do you do with the one in the bottom?
We just multiply 2 by 4.
Multiply it by the reciprocal. So 2 pi divided by 1/4 is 8 pi. So the cycle there just got 4 times as big. Right? So if you wanted to think of it in degrees, this graph has to go all the way to 1,440 degrees on the x-axis before you get a full cycle. It's much longer now. 4 times as long. Any question on that one? Now, what if I did this? What would be the period now?
Wouldn't the period be the same, but it would move over 6?
It would move up 6, but the period would still be the same. Putting a plus 6 there has no effect on the period at all. What if I did this? What would be the period now? Same thing. All that does is triple the height. But tripling the height has nothing to do with stretching it left and right. So it doesn't matter if you put a number here, if you put one at the end, even if you did a phase shift, the only number you have to focus on for the period is the number in front of x. So don't get confused by any of the other numbers. You do all these problems I just showed you the same way. Any questions on that?
How many questions on the test?
10. So there's 6 graphs, and then there's 2 questions that say find the period, and then there's 2 questions that say find the amplitude. So let's say I gave you this last one right here. What's the amplitude of that one? 3. Yep. What if I did this? What's the amplitude of that one? Still 3. Yep. So 2 questions will say find the amplitude, so you want to know what number to focus on. 2 questions will say find the period.
Wait, so the amplitude's always the one in the front?
It's the absolute value of the one in front.
Yeah.
Yep. And the period, you have to do the calculation. 2 pi divided by the number in front of x. A lot of people just put the number in front of x and say that's the period. No, it's not the period. You got to divide it out. All right, so let's take a look at what that would sound like. So when we stretched and compressed it up and down, what happened to the sound? Remember? Yeah.
Didn't it sound like it was moving?
I think that was more the phase shift. When we did the phase shift one.
Was it like louder?
Louder. Yeah, it got louder or it got softer when we stretched it up and down. So, softer, louder. That was yesterday. So today, we're going to stretch and compress it left and right. What do you think that's going to change? Christian?
Pitch?
Yeah, the pitch of it, or the frequency of it. So, if we play that sound, okay, that's 1,000 hertz sound. So, if I go up, as I start to drag it to the right, you can see what's happening to the wave. It's starting to compress. So now that was 1,000. This is a little above 4,000. So getting higher pitched. Eventually, we'll compress it so much we can't even see it really anymore. Now it's getting kind of hard to see. So this is up at a little over 8 kilohertz or 8,000 hertz. So it's a higher pitched sound, but it's still it's a little under halfway of what perfect hearing would be. What you can hear, kind of the upper limit. So up around almost 12 kilohertz. Anyone that can't hear that one? Yeah, you can still hear it. It starts to get harder to hear as it gets higher pitched. Sometimes you need a little more volume. We go up to about 14,000. So you can still, anyone couldn't hear that one? Yeah, I can still hear that one, but that's much higher pitch. Up around 16 is where I usually I lose that. Yeah. For me, that one was gone. So up around 16, just what happens. You lose the high end of hearing. And then if you go even higher, like go all the way to 19 kilohertz. Anyone that didn't hear that one? Yeah. I mean, you can hear a little buzzing. That's not the sound. The sound would be like extremely high. Again, you bring it back down. Some people might start.
Yeah.
So that's a much higher pitch. All right, so those are your high pitch sounds. As you compress it, as you stretch it, we start to get into lower pitch sounds. So this would be pretty low. So pretty low. If I do it from the computer, it's a little easier. We go a little lower. Let's go down to about 100. A little bit lower, but notice what's happening is it's starting to almost vibrate. Where the high pitch sounds, you didn't really feel vibrations as much. But the lower pitch sounds, you can go. And then the lowest I can go, roughly with the speakers that I have, is about 45.
Sounds like a beat.
And you notice something was vibrating somewhere. So what that is that's resonance. So it's the exact frequency that there's some object in the room that vibrates at 45 hertz. And that's, I'm not sure where it might have been. Maybe the lights or the vents. Sounds like it's over there somewhere. As you go up, you might hear different things starting to vibrate. So that one kind of stopped now a little bit. Now, something else now. Around 53 hertz, I'm getting something else to vibrate.
Oh no, it's shaking.
So those are just the natural frequency that different objects vibrate at. And they do that with glass sometimes. Like glass has a frequency that it vibrates at, depending on the shape of it and the size of it. And they do it a lot with like a wine glass, where if you play the exact frequency that it vibrates at loud enough, the glass will start to vibrate and eventually it'll break.
Oh, that's the reason why when women sing, they can like break glass.
Yeah, it is possible, yep. But you have to play the exact frequency. Because notice when I was down at like 45 hertz, you didn't, like I heard something different start vibrating over here. So that's not much of a change. So you have to play the exact frequency and you have to be able to hold that exact frequency. If you change it just a little, it won't work. So, yeah. But that's the idea of changing the pitch. You get changes in the frequency. Any questions on that? All right. So finding the period, a few examples, and now we'll look at what happens to the 5 coordinates in the table when we do a period change. All right, so we're stretching and compressing left and right. So what's changing when we stretch and compress left and right? Which values? The x's. So that means the y's are staying the same. Okay. Unfortunately, if the y's are staying the same, those are the easy ones to work with. So we're not going to get to work with 1s, 0s, and -1s today. Those are going to stay the same. We're going to have to work with the x column. And there's a couple different methods to find the new x's, depending on the complexity of the problem. Certain methods are easier than others. I'm going to show you one method that works for us. In particular, this method works well because we never combine transformations. Like you'd never have a problem on the test like this. That's a combination of a phase shift and a period change. It's being shifted by pi, and the period is being compressed. So you wouldn't have something like that. If you have problems that get into a little bit more complicated stuff, the method I'm going to show you doesn't always work. In fact, it wouldn't work. All right, for that problem right there. Okay, but since we don't have to get into that, I can kind of show you a simple method that'll work for the ones that you're doing. All right, what's the first x coordinate in either the sine or the cosine table? Doesn't matter which table.
0.
0. Now, if you take 0 and you stretch it, make 0 bigger, multiply it by a number, what do you get?
0.
0. If you take 0 and compress it, multiply it by a fraction, what do you get?
0.
0. So the first x coordinate is always 0. Now, why wouldn't it work for this one? Because if you do that, the first x coordinate is not 0. It's been shifted. You've taken the graph and you shifted it pi units to the left. So the first x coordinate is no longer 0, which means if you stretch or compress a number that's not 0, you get a number that's not 0. So this method wouldn't work for that problem. All right, so we got the first x coordinate. Okay. The last coordinate, that's the end of the cycle. So the fifth coordinate, or what I'm calling, like if I drew it out, first one is 0. The one that I just filled in, the last one, that's the end of the cycle. So to find the end of the cycle, use your formula that gives you the length of the cycle. That'll tell you where it ends. So now we've got the beginning, we've got the end, and the middle is halfway between the two. So if you know the beginning and you know the end, how could you find mathematically the number that's right in the middle of the two? Yep.
2.
What's that called when you do that?
Division.
Well, division, one more thing you got to do.
Multiply by half.
Yeah, you're finding like an average, right? If you want to know what's in the middle of two other numbers, add them up and divide by 2. I didn't write out how to do an average. I'm assuming you guys can remember that. But the third x coordinate is the average of the first and the fifth. All right. Yep, Joe.
If it's just 0 every time, wouldn't it just always be the average of whatever equals t?
Well, it would always be, you mean this end point here?
Yeah, it's always half.
It's always half, yeah.
Half of what that number is.
Yeah, this number is always basically half of t. Because to get the end value, I'm sorry, I was off a little bit. That number is always half of t. Because you're always averaging a number with 0. Anytime you average something with 0, you just take half of it. Like if you had 100, and you got a 0, your average is 50. Just take half of the first number. So yes, that's always going to be half t. Now, how do you think you would find the second x-coordinate, which is exactly halfway between the first and the third? Yep.
Half of the middle.
Yeah, you're going to average again. Average the first and average the third. But again, you're averaging something with 0. So really, just take half of the third. So that one is really quarter t. Or you can just think of it as the average of the first, which is 0, always, for the kind of problems we're doing, and the third. Yep.
Well, the next one will be 3/4 t.
So the next one, let's see. Yep. Yeah, because each one is a quarter point of the cycle. So yeah, that's really good if you notice that. Quarter of the way through the cycle, halfway through the cycle, 3/4 of the way through the cycle, t, all the way through the cycle. Right? Or another way to think of it is to get this one, it's exactly halfway between the third and the fifth, so it's just the average of the third and the fifth, which will be 3/4 of the way through the cycle. Okay. So beginning is 0. To get the end, you use your formula for t, and then the rest of it, you can kind of think of it the way Joe said, or you can just think of it as averaging. Average 3 times to get the last 3 coordinates. Okay. Any questions on that? Okay. So that's probably a good place to stop because we have to go down and do the pictures. So when we come back up, we'll do a couple examples and see what else we have time for. Okay, so first one we'll take a look at is sine 2x. Okay, so just like always, first thing we want to do is make our table. And what values, well, how do we know this is a period change? How come it's not a phase shift, vertical shift, amplitude change?
Parentheses.
All right, so what makes it a period change?
There's no parentheses around the 2x.
What if I did this?
I think it's the same.
That's still the same problem. So even if we put parentheses, it's still the same problem. So what makes it a period change then? Obviously the parentheses are not, because I can take them out and it's still a period change. Yeah.
You're multiplying just by the x, not by the sign.
Yeah. We're multiplying by a number in front of the x. That's what makes it a period change. So period change stretches and compresses left and right. So what values are not affected at all? The y's. So we're going to keep the y's the same. Unfortunately, those are the easy numbers to work with. We don't get to work with them this time. All right, but when we do a period change, we already know our first x value for the kinds of problems we're doing because they're relatively, they're one step. You're only going to do one thing per problem. So only one number. The first x value is always what?
0.
In this kind of problem, it's always 0. So we've got the first one, and then after I get that one, what's the next one I want to find?
What?
So I've got the first one. What's the next one I want to find? The fifth one. How do I get the fifth one?
You do the 2 pi over the t.
Yep. 2 pi over, what's it going to be in this case? Omega, which is 2 in this case. So that's going to tell me the length of the cycle, or where I end. So where do I end? I could write it this way, but I can reduce that to what? Pi. Now, I've got the beginning, I've got the end. What's the average of 0 and pi? Pi over 2. You're really just taking half because you just averaged with 0. Well, now we're going to average with 0 again. What's halfway between 0 and pi over 2? Pi over 4. And now the last one, this is the 3/4 point. The beginning, quarter, half, 3/4, all the way. All right. So now we have to find the 3/4 point. And there's a couple ways to do it. If you notice a pattern, you could go with that. Or if not, we'll just do an average. Yeah.
Could you multiply pi by 3 or multiply it by 4/3?
3/4. You could multiply it by 3/4 because it's the 3/4
Oh
point.
yeah, I was thinking.
Yep. So you could multiply it by 3/4 because you know this is the full cycle. Right there is 3/4 of the way through the cycle, so it's 3 times pi over 4. Or if that's kind of confusing and you want just a method with averaging, take pi over 2 plus pi. But when you want to average two things, you have to add them up and then divide by what?
2.
Divide by 2. Actually, you know what? So I don't have a fraction over a fraction. Dividing by 2 is the same as just taking half of it. So I'll just write it that way. But to add those up, what's my common denominator? 2 times 2 times 2. So the answer is half of something over 2. What's 1 pi over 2 plus 2 pi over 2? 3 pi over 2. And then when you take half of it, 1 times 3 gives me 3. 2 times 2 gives me 4. 3 pi over 4. Okay. The pattern, if you wrote everything with a denominator of 4, this is 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4.
Yeah, wouldn't it have been way easier to just times pi by 3/4?
Yeah, if you realize that it's the 3/4 point, you can do that as well. I mean, for me to average them, because I just would do the common denominator in my head, I would just say, oh, 3 pi over 2, double the denominator, it's 3 pi over 4. So it's, depending on how you think things through in your head, either method could be just as fast.
So you can just multiply them by 4, 1/2, and 3/4.
Yeah, you could take all the original ones and multiply them by 1/4, 1/2, and 3/4. Yeah. Sometimes the averaging is actually going to be faster because, well, the numbers are nicer. So I'll show you that one in a second. Okay, but any questions on this one?
How do you graph it?
Oh, how do you graph it? Yeah, so we still have to graph it. So we're going to label our x-axis. Now, the spacing here is not 90. This is 0, 45, 90, 135, 180. They all have gaps of 45 between them. Okay, that's the spacing. Well, the gaps are all the same. So you can use those labels on your x-axis. The only thing you have to be careful when you label an x-axis is you label consistently. Don't change your scale. So pi over 4, pi over 2, 3 pi over 4, and pi. The pattern would be more obvious if you wrote everything with a denominator of 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. But we don't leave it as 4 pi over 4 because we can reduce it. Reducing it makes the pattern less obvious, but you should reduce it. Okay. 1, negative 1. And now we just graph. So 0, 0, pi over 4, 1, pi over 2, 0. -1, here's where I probably should have moved my labels down a little bit. We've talked about that. And pi back at 0. There's your graph. Okay, and that has been compressed. This graph did a full cycle by the time it got to pi. The normal graph does a full cycle once it gets to 2 pi. Okay. So in the normal graph, you would only be halfway through the cycle, right, at this point. Okay. Any questions on that one? Okay, let's try this one. Cosine of 1/4 x. Now, we already found the period of this. So I'm going to go back in the notes in a minute, but we already did this problem. We just didn't graph it. So it's a period change. So our y's are going to stay the same. Make sure you copy the y's from the cosine table, not the sine table. For period change, first x is always what? 0. And what did we get earlier in the notes when we did 2 pi divided by 1/4?
8 pi.
8 pi. We already did that right here. We had a 1/4. So we already went through how to get 8 pi. So now the averaging here is actually going to be faster, the fastest way to do it. What's halfway between 0 and 8 pi?
4 pi.
Halfway between 0 and 4 pi? Halfway between 4 pi and 8 pi.
6 pi.
So the averaging can work out faster if the numbers are nice. Okay. Or you can think of it as the way Joe or someone mentioned that, I think it was Skylar too. Quarter, multiply the original by a quarter, by a half, and then by 3/4. Okay. So now the spacing here is 0, 360, 720. It's going by plus 360 every time. So it's consistent. And it has to be because that's how we found these numbers. We found things that were exactly in the middle. We averaged. So it's spaced nicely. 2 pi, 4 pi, 6 pi, 8 pi. The 1 and -1 is not going to change at all today. All I'm going to do is I'm going to move these down. All right, so we're at 1, 0, -1, 0, 1. So 1, 0, -1, 0, back to 1. And there's your graph. Any questions on that one? Right, so that's been stretched a lot. It's been stretched out 4 times as much. It doesn't look like it's been stretched on paper because I changed my scale. Okay, if I didn't change my scale, then I'd have to draw this huge. It would take up like the whole board width. Okay, that's why we change our scale. Okay, let's look at this one. So y equals sine of pi over 2 x. Okay, what kind of problem is this one out of the 4 that we've studied? Phase. So phase means you are adding or subtracting inside the parentheses. So are we doing that here? No, so it's not a phase shift. It's still a period change. You're multiplying by a number in front of x. 3.14 divided by 2 is 1.57. So it's just like 1.57x. But leave it as pi over 2 and we'll see what happens. So 0, 1, 0, -1, 0. First x value?
0.
0. What's my formula to find where the cycle is going to end? Well, t equals 2 pi over, what's omega in this case? Pi over 2. How do I divide those two? Yep.
Multiply by the reciprocal.
Multiply by the reciprocals. 2 pi over 1 times 2 over pi. What happens when I multiply that out? Pi's cancel. So what do I get for the ending point of my cycle? 4. 2 times 2 gives me 4. So this one actually, it has a nice ending point. This is the only graph we've done all week. It's not going to have any pi's in the x values. And now the averaging should be pretty fast. The third x coordinate would be the second one, and the third one, 3. That's it. This is also the only problem where technically you don't have to label your x or your y axis, because I would go by 1s on both of them. If you want to, you still can. But this is the only time this week where this has ever happened. Okay. 1, negative 1. All right. So we got 0, 0, 1, 1, 2, 0, 3, negative 1, 4, 0. So that graph has been compressed a little bit. Okay. Normally, to do a cycle, you've got to go all the way to 2 pi, which is 6.28. This graph is doing a full cycle by the time it gets to the number 4. So it's cycling a little faster, not a lot faster. So any questions on that?
Wait, that where you did the part to find where you end, did you have to do that for the last one?
I did, but we had already done it earlier in the notes. So we had already done the calculation 2 pi divided by 1/4. So we just looked back at the one we already did. Yep. Any other questions on that? Okay, so again, on the test tomorrow, there'll be 6 graphs. Obviously, we only get 4 transformations, so 2 of the transformations I'm going to double up on and give you a couple of them. So 6 graphs. Each graph will have 10 points for the table, 2 points for the sketch, and then we'll have 4 multiple choice questions. 2 of them are going to say find the period, 2 of them are going to say find the amplitude. And we practiced finding the period in the notes today. We practiced amplitude. Well, actually, we did practice amplitude today a little too, but we did that yesterday. Any questions on that?
You always have a review sheet.
Yep, you gotta have a reference sheet for it. Yep. Any other questions on that? All right. So the homework tonight will be a worksheet just like the other ones. We have a little bit of time, so I might have time to do the cell phone thing. Probably not anything else. So I'll do that and see what we have time for after.